Groechenig from University of Vienna, who will talk about Marcinkiewicz-Zygmund families for polynomials in Bergman, Hardy, and Fock spaces. Please.
Well, hello, everybody. It's again an interesting feeling to sit at my own desk and talk to mathematicians in Europe, North America, Asia. And I have to say good morning or good afternoon or even good night. So topic is Marcinkiewicz-Zygmund families for certain spaces of analytic functions. And before starting, I want to say that's joint work with Joaquim Ortega-Cerda from University of Barcelona, who talked yesterday. The problem I'm going to address is fits well into this week on sampling and interpolation. So I chose this workshop rather than next week's, and I'm very happy that I am able to, or that I am able to contribute. So, chapter 1, Marcinkiewicz-Zygmund families. So let me first talk about the abstract problem. I think that it's a good sequel to Andreas Hartmann's talk. So we are looking at a reproducing kernel Hilbert space on some set X with respect to a measure mu. And reproducing kernel Hilbert space means that point evaluations are given by a linear functional k sub x. So that's a function, and I can write the kernel as a function of two variables. And now the goal is to investigate sampling sets for this reproducing kernel Hilbert space. Investigate and construct sampling sets. So what we're after are sampling inequalities where the sampled L2 norm is equivalent to the overall L2 norm of F in that reproducing kernel Hilbert space. That's usually an infinite dimensional problem. And one of the ideas that may appear simpler is to replace that problem by a sequence of finite dimensional problems. So in an abstract setting of a Hilbert space, we would consider a sequence of nested finite dimensional subspaces. I call them P sub n. And since these are subspaces of a reproducing kernel, each of these subspaces comes with an intrinsic reproducing kernel. So if I just take a function in a subspace Pn, then certainly the point evaluation is a continuous functional, but I can choose this functional to be in the subspace itself, okay? So that's the reproducing kernel that belongs to that subspace. Well, this is nothing but the orthogonal projection of the reproducing kernel onto that subspace. Now, the hope is that perhaps the investigation of sampling in finite dimensional subspaces is easier. After all, these are finite dimensional problems, and perhaps it's just a problem of linear algebra. Okay, so let's see how that works. So this setup motivates the following definitions. So for each of these subspaces, we have a different sampling set, lambda n. And now we call a family or an array or a sequence of finite subsets, lambda n, a Marcinkiewicz-Zygmund family for this sequence of subspaces if there exist universal constants that are independent of n, such that we have a sampling inequality on each of these subspaces. Again, here in the middle, you have the sampled L2 norm of a function p in the nth subspace. This L2 norm comes with a weight, and that weight is the intrinsic reproducing kernel on the diagonal at the sampling point lambda. The sum goes over the nth layer of the Marcinkiewicz-Zygmund family, and this sampling inequality should hold for all elements in the nth subspace. Okay, so here I have circled the three ingredients that depend on the n: subspace, reproducing kernel, and sampling set. What should not depend on n are the two constants. It's essential in this definition that these constants are independent of n. So now, why would we look at this particular weight? You have seen that before. Well, these are the intrinsic kernels. They belong to the space itself and not to some ambient superspace. Secondly, if you look at, point evaluation in the subspace, then the norm of the reproducing kernel is just the reproducing kernel on the diagonal. So what you divide here is just the norm of the reproducing kernel. So in a sense, equivalently, you take the inner product of P with the normalized reproducing kernel, intrinsic reproducing kernel at the point X. And so we could say this is a sampling inequality, weighted sampling inequality for the nth subspace. In the language, say, of next week's workshop, this is just a frame inequality with frame elements that all have norm 1. So these are two different languages for the same thing. And that's one of the explanations for this particular use of weights. That's suggested already by Shapiro and Shields, I think, in a paper of the 1960s or 70s. Okay, so that's the general setup. And now let's just look at the most basic cases. The set X would be a subset of the real line or the complex plane. The most natural sequence of nested subspaces would simply be the subspaces of polynomials of degree n. And if you now take the closure of all polynomials with respect to the ambient L2 space, then you get a space of analytic functions, some kind of Bergman space. So fine. Now let's be even more specific, and let's consider the domain to be the unit disk in the complex plane, and the ambient space we're dealing with is the classical Bergman space on the unit disk. So these are all analytic functions on the unit disk. The norm is just the L2 norm with respect to the area measure. So I just recollect three facts. The monomials are orthogonal, just do polar coordinates. And if you normalize suitably, so the normalization factor is square root k plus 1, then you obtain an orthonormal basis for Bergman space. Now, if you take polynomials of degree n, then you calculate the reproducing kernel for polynomials of degree n by taking, let's call them tensor product of the basis elements up to degree n. So we have square root k plus 1 z to the k times square root k plus 1 w bar to the k. So here you get the formula for the reproducing kernel. And if you do the algebra, you find some expression for the intrinsic reproducing kernel. That's the reproducing kernel just for polynomials of degree n with respect to the norm of Bergman space. If n goes to infinity, okay, these are points. So these are points in the unit disk. So n going to infinity, this goes to 0, this goes to 0. So in the limit, you obtain the Bergman kernel for the unit disk. Okay, so this is what we need. And now I can already state the theorem. So roughly speaking, there's a relation, deep, intimate relation between Marcinkiewicz-Zygmund families for polynomials in Bergman space and sampling sets for the full Bergman space. If you start with a sampling set for a full Bergman space, then finite sections of the sampling set yield a Marcinkiewicz-Zygmund family. So precisely finite sections, you take, so you start with a sampling set for the full Bergman space. So you have a sampling inequality for all functions in Bergman space. And the way, so it's similar to this one here, except that all functions in Bergman space, and you take, so you delete all the n's, and you have a sampling inequality for all functions in Bergman space. Here you would have a lambda, and here would have the Bergman kernel. Okay, so you start with that. Now you truncate, you just take those points of the sampling set that are inside a disk of radius 1 minus gamma over n. So these are finitely many. And so you do that for every n. This depends on the degree of the polynomial. So as n gets larger, this disk exhausts the unit disk more and more, so you get more points. And so depending on n, this sequence of finite subsets of the original lambda form a Marcinkiewicz-Zygmund family for polynomials. So this means, to recall once more, for each polynomial subspace, you have a sampling inequality. The lambda n's of the Marcinkiewicz-Zygmund family are obtained by, say, taking a finite subset of the original sampling set. You use the intrinsic reproducing kernel. This is true for polynomials of degree n, and the constants are independent of the degree. So this gives you a way to move from sampling sets to Marcinkiewicz-Zygmund families. There is a converse. Suppose you have a Marcinkiewicz-Zygmund family. So this is a sequence of finite sets. You can associate to any sequence of finite sets a weak limit. Okay. Either you take the sum of, so either you take the sum of point measures on lambda n and take a suitable weak limit of these measures, or you take these, or you take the original definition, I think it goes back to Berling, take the intersection with an arbitrary compact disk in, this too is a footnote, not a square. And then you have a set, a finite set, and you'll require that this finite set converges to some other set, and the convergence should be in the Hausdorff metric of compact sets. The underlying metric would be the pseudo-hyperbolic metric on the unit disk. So all this can be worked out explicitly, and I think is known. So with these explanations, assume you have a Marcinkiewicz-Zygmund family for polynomials in Bergman space. Now take an arbitrary weak limit of this sequence of subsets, then you obtain a sampling set for Bergman space. let me go back. Suppose you have the sampling inequalities for arbitrary, for polynomials degree n. Now you let n go to infinity, then you have lambda here. If n goes to infinity, you have the Bergman kernel, and you obtain a sampling inequality for all. So here you would have A2. So you obtain, by taking a limit of this sequence of samplings inequalities, you get a single sampling inequality for the full Bergman space. So let me pause here for a moment and mention 3 items. So this strategy gives you a way, at least in theory, to prove sampling theorems for infinite dimensional spaces, in our case, Bergman space, via finite dimensional versions. Finite dimensional versions is what in our language are called Marcinkiewicz-Zygmund families. For band-limited functions, I did something a long time ago, approximation of band-limited functions by trigonometric polynomials. At that time, I didn't even know that this was called Marcinkiewicz-Zygmund families. But so my interest goes far back to a different time of my mathematical life. So these 2 theorems that relate Marcinkiewicz-Zygmund families to sampling theorems tell you that both problems possess the same difficulty. So the construction of a hierarchy of sampling theorems for finite dimensional spaces with uniform constants and the construction of sampling sets for the infinite dimensional space, these are problems of equal difficulty. Now, what have we gained? Well, in the case of Bergman space, sampling sets have been characterized completely in a groundbreaking paper by Christian Seip in 1995. So the one part, the infinite dimensional part of the problem is already solved. And now if you go back, so this assumption here is verifiable in principle, and it's known how sampling sets in Bergman space look like. So with this theorem, we automatically obtain a construction for Marcinkiewicz-Zygmund families. Going the other way is equally difficult, but we don't even know how to do that. Okay, so this is essentially the fundamental connection that I want to communicate in this talk. Now, there are a few elements of the proof that I want to highlight so that you get a feeling what the main ideas are. In particular, I want to show where this the radius 1 minus gamma over n comes from, how it arises from in the analysis. So first idea is localization of energy. So the norm on Bergman space is the area measure on the unit disk. Now, for the finite dimensional subspace of polynomials of degree n, you can restrict to smaller disks and still obtain an equivalent norm. So let's do this calculation. We take a polynomial of degree n, coefficients a sub k, and we compute the L2 norm restricted to a disk of radius rho. Okay, so I plug in the polynomial, work out the sum. I obtain inner product of the monomials. And the point is that and here. Monomials are orthogonal on all centered disks, not just on the unit disk, they are orthogonal on all centered disks. So only the term k equal L survives. And you end up with this sum here after doing polar coordinates. So you get the integrals over r to the 2k times r dr. If you work that out, you get 1 over 2k plus 2, cancels with the 2, the pi cancels, and what you obtain is this sum here. Rho is less than 1, so the smallest term here is for the largest coefficient. So you obtain that so you pull this out, and the rest is just the Bergman norm of the polynomial. So we obtain that on a disk of radius rho, the 2 norm is bounded by a power of rho times the original norm. Fine. Now we do that now we vary the degree. Okay, we vary the degree n. And so we write rho, and we want, so we write rho sub n instead of rho, and we obtain this here. First goal is to choose the radius independence of the degree in such a way that we get a uniform lower bound that's independent of the degree of the polynomial. And so we need that rho sub n to the 2n plus 2 is bounded away from 0. And okay, now you see this works precisely when you choose rho sub n to be 1 minus gamma over n, where gamma for now is a fixed constant. So the gamma essentially measures the annulus in the unit disk near the boundary that you omit. This is a first explanation where the 1 minus gamma over n in the theorem, why this radius appears in the theorem. Okay, we just look at the left-hand side. So this is the whole unit disk, and there's a bulk region of radius 1 minus gamma over n, where the energy of polynomials of degree n is concentrated. This radius is 1 minus gamma over n. The gamma over n indicates the distance to the boundary. Okay. So the second ingredient is the comparison of kernels. We compare the intrinsic kernel, intrinsic for polynomials degree n, to the Bergman kernel. I don't want to display the formula for the intrinsic kernel again, but the insight that you get after some estimates is that, again, on the same disk where the energy is concentrated for polynomials of degree n, also the intrinsic kernel on the diagonal is comparable to the Bergman kernel itself. Outside, so that's near the boundary of the unit disk, the intrinsic kernel behaves like n squared, whereas the Bergman kernel explodes to infinity. So in the bulk region, intrinsic kernel and Bergman kernel are comparable. Outside, they are not related at all. Again, it's important that we get the 1 minus gamma over n as the division between the bulk region and the boundary. Third ingredient are tail estimates. So F is analytic, so F absolute squared is subharmonic, and the submean value property tells you that you can that the point value valuation is dominated by a local average, and we will need that for the sampling points near the boundary. So we take the sampled values of a polynomial of degree n outside the bulk region. We normalize with the extrinsic reproducing kernel. We take the sum. So you take Euclidean disks of radius rho at the sampling points. Then the union of all these disks certainly contained in the annulus outside, well, gamma plus delta over n. And now you can choose the n in such a way that the energy outside the bulk region is less than epsilon times the total energy. So you need tail estimates. And finally, I can sketch you one of the arguments, namely the argument that sampling implies Marcinkiewicz-Zygmund family. So the assumption is that we have a sampling set for Bergman space. Now we restrict to the subspace of polynomials of degree n. And we first do away with the tail region, the region near the boundary. So we take all points outside this disk of radius 1 minus gamma over n. So always the degree tells you which radii to choose. So we use the tail estimate, and choosing gamma large enough, small enough, we can control this part of the entire sampling set by epsilon times the norm, times the norm of the polynomial in Bergman space. And then we want sampling. So then we look at the sampling inequality for all the points in the bulk region for polynomials of degree n. So now we use the intrinsic reproducing kernel. First observation, in this region, the intrinsic kernel is comparable to the Bergman kernel. Okay, so I replace the intrinsic kernel by the Bergman kernel. So the sum is still over the points in the bulk. And now I write this sum as the sum over the entire sampling set minus the sum over the points outside the bulk region. This sum here is bounded below by 8 times the norm of the polynomial, simply because I have assumed that we start with a sampling set for the entire Bergman space. And this term is small by tail estimate. So we get a lower bound, lower sampling bound that's independent of the degree n. The degree enters in the use of the intrinsic reproducing kernel and in the choice of the appropriate radius. Upper bound is similar, and there are plenty of other details to check, but I hope that you can see how this choice of radius comes in and what kinds of considerations you have to make. Sorry. Okay, so this is Bergman space. For some reason, we started with Bergman space when Kim and I started to discuss this problem of Marcinkiewicz-Zygmund inequalities. From my background in time frequency analysis, it's actually Fock space would be a much more natural example. We have been looking at that only later, and I briefly go over the question about Marcinkiewicz-Zygmund families in Fock space. So in this case, we look at entire functions. So analytic on the entire complex plane, and we use Gaussian measure. So this is the Fock norm. Again, monomials are orthogonal, and with proper normalization, you get an orthonormal basis. The reproducing kernel is reproducing kernel for polynomials of degree n. Well, you sum the basis elements with respect to the two variables up to n. So what you obtain is a partial sum of the exponential series up to index n. And this is the intrinsic reproducing kernel. What is important for later is that you can write it as exponential times incomplete gamma function. Well, if you take n to infinity, then you get the exponential function at pi w z, and this is the reproducing kernel for Fock space, as you have probably heard several times already this week. So these are the main ingredients required for the analysis. What is important and what I want to point out is this formula for the intrinsic reproducing kernel. Intrinsic reproducing kernel is equal to the reproducing kernel times the incomplete gamma function at pi zw bar. Now, incomplete gamma function at n+1 a is, well, it looks like the definition of the gamma function, except that you start the integration at a and not at 0. You can extend that, you can extend the incomplete gamma function to complex plane, complex variables in both arguments, but this is a different story. Okay, so now I can already, well, maybe let's go back once more. So we have reproducing kernel, we have the reproducing kernel, we have the intrinsic reproducing kernel, we have sampling sets in Fock space, and we have sampling sets for the polynomials of degree n. And sampling inequalities with uniform bounds are called Marcinkiewicz-Zygmund families. So same setup as before, except that our domain is now the complex plane, and the measure is the Gauss measure. Okay, now the result is almost identical. Let's start with a sampling set for Fock space. And now the interesting part is, okay, what's the bulk region? How do we have to choose the radius of the disk appropriately so that the finite sections of the sampling set form a Marcinkiewicz-Zygmund family? So finite subsets of the infinite sampling set for Fock space that give us sampling theorems. And this is what we came up with. These are centered disks of radius rho sub n, such that the area of this disk is slightly larger than n. It's n plus squared n times tau, and tau is a fixed parameter that we have to choose large enough. So again, if you go through the proofs, this is the size of the disk on which most of the energy of the polynomials of degree n is localized. And this is also the size where you can compare the intrinsic reproducing kernel to the reproducing kernel of Fock space. So sampling set for Fock space implies existence and construction of Marcinkiewicz-Zygmund family for polynomials. And conversely, assume you have a Marcinkiewicz-Zygmund family for polynomials, take a weak limit, then you obtain a sampling set for Fock space. I have shown the ideas for Bergman space, so the proof would be similar. What is different and what caused us a lot of headache is the study of the asymptotics for the incomplete gamma function. It's a very interesting special function, and I think Tricomi called it the Cinderella of all special functions. It occurs in so many applications, and the asymptotics is rather subtle. So to summarize this chapter, again, we see a correspondence, close relation between Marcinkiewicz-Zygmund families for polynomials in Fock space and sampling theorems for polynomials in Fock space. Again, I should say the problem is already solved. Sampling sets for Fock space are fully characterized by the work of Yuri Lubowski. I think he will speak tomorrow, and of Christian Seip. These results go back to the 1992, actually. So again, the problem of Marcinkiewicz-Zygmund families is understood modulo a substantial theorem about sampling in Fock space. Let me say a little bit more. I mean, when you look at polynomials of degree n, then it's clear every polynomial of degree n is uniquely determined by n+1 points. And so you have a sampling inequality. If you look at sampling inequalities with uniform constants, then of course the question is, how many additional points do you need in order to guarantee that the sampling inequalities are uniform? So one insight is that basically you get as close to n+1 as you want. You can construct Marcinkiewicz-Zygmund families with n+1 times 1 plus epsilon for arbitrary epsilon predetermined. Well, you just choose a sampling set that has density between 1 and 1 plus epsilon, and then you have this number of points in balls in disks whose area is n. Yeah. However, okay, so you need slightly more than n+1 points in order to guarantee uniform sampling inequalities for polynomials. However, you cannot do the optimal thing. There is no Marcinkiewicz-Zygmund family with precisely n+1 points. Proof is indirect. If such a Marcinkiewicz-Zygmund family would exist, then you take weak limit, you get a sampling set for Fock space by the theorem I showed you. And at the same time, this would be an interpolating set for Fock space. And it's known that such sets do not exist. This is a contribution maybe for next week, possible formulation for time frequency analysis. This time frequency analysis deals with time frequency shifts of a given function and their spanning properties. Now, whenever you try to look at spanning properties of a shift and a modulation of the Gaussian, then you usually map it via the Bergman transform to a problem in Fock space. So the time frequency shifts of the Gaussian are mapped to the reproducing kernel in Fock space. Monomials, the Hermite functions are mapped to the monomials. So since we started with Fock space, I take the inverse Bergman transform. This goes from Fock space onto L2 of the real line. The subspace of polynomials of degree n is mapped to the span of the Hermite functions up to n, and the inverse image of the reproducing kernel of Fock space are the time frequency shifts of the Gaussian on R. And just translating this, taking this dictionary, you can make the following assertion. Assume that you have a sampling set for Fock space. In the language of time frequency analysis, the Gaussian with this set forms a Gabor time frequency shift of the Gaussian with the sampling set is a Gabor frame. Okay. Then the time frequency shifts of the Gaussian truncated to all points inside the disk with area n plus squared n tau. They form a frame for this finite dimensional space that's spanned by the first n plus 1 Hermite functions. And the bounds are independent of n. That's the most important thing. I always thought that this might be of interest in time frequency analysis, so I insist that this is perhaps an interesting reformulation of the theorem about time frequency shift, theorem about Marcinkiewicz-Zygmund families in Fock space. So, last chapter, let's go back to the unit disk and just change norm. Let's look at Hardy space. So this is the set of space of all analytic functions on the disk, but this time I choose a different norm. This is the norm, the L2 norm of the boundary values of the disk. I would say this is convenient for us. So it's the L2 norm on the torus. Again, monomials are orthogonal. In fact, the monomials form an orthonormal basis for Hardy space. And the intrinsic reproducing kernel for polynomials of degree n. Okay, you again sum the orthogonal basis, tensor with an orthogonal basis from 0 to n. And what you obtain is this expression here. As n goes to infinity, you obtain the reproducing kernel for Hardy space. Okay, now we could start to ask the same question. How about Marcinkiewicz-Zygmund families in Hardy space? And here, to our surprise, there's something completely different happening. There's a basic fact about sampling in Hardy space due to Pascal-Thomas. If you have a sampling, if you have a function in Hardy space that satisfies sampling inequality, okay, that would be the sampling inequality in Hardy space, then automatically this function must be identical 0. So there is no sampling inequality of this type in Hardy space. There are different notions of sampling for Hardy space, but the way we understand sampling inequalities, sampling theorems in a space or in a reproducing kernel Hilbert space, there is no such object for Hardy space. And therefore, we cannot expect an analog of the results that I showed you for Bergman space and for Fock space. However, we found a way to construct Marcinkiewicz-Zygmund families for Hardy space. And this construction is a bit different. You start with the torus and L2 of the torus. Now, in L2 of the torus, you have, well, the natural subspaces are either trigonometric polynomials of degree n, or what's interesting for us are the algebraic, so the analytic polynomials of degree n in the torus. So only positive powers. And there you can start, there you can construct Marcinkiewicz-Zygmund families. In this case, the weight is for degree n is always 1 over n. And so let's assume, and you take the sampling points on the lie on the torus, okay, for polynomials, so no problem. And I call these, the points on the torus are in the nth layer, I call e to the I nu n k. So in the nth layer, we have certain points labeled by k, and we assume that we have sampling theorem for analytic polynomials on the torus. Now, what we do is we move these points on the torus inside the disk, and we move them inside the disk arbitrarily, but only in an annulus of radius 1 minus gamma over n to 1. Okay, given the points on the torus, we move these points inside the unit disk by arbitrary radii in this interval here. Then this family of points obtained in this way form a Marcinkiewicz-Zygmund family for the torus. Two pictures. One, okay, let me show you the picture. So here we have the sampling points for polynomials of degree n for the torus. And what we do, and we have the annulus of width gamma over n, and we move these points from the boundary of the unit disk into the unit disk, into this annulus. The radius can be arbitrary as long as we stay in this annulus. So we start with Marcinkiewicz-Zygmund family for the torus, and we end up with a Marcinkiewicz-Zygmund family for Hardy space. Here is a comparison that perhaps explains a bit the analogy and the difference to Bergman space. In Bergman space, the norm lives on the entire unit disk, and the norm of a polynomial lives in the bulk region. So that's a disk of radius 1 minus gamma over n, n always the degree. For Hardy space, the norm is actually concentrated on the unit circle, or you can thicken the unit circle a little bit, and the way how much you can thicken it is again this radius 1 minus gamma over n. So the energy of a function in Hardy space lives essentially on such an annulus. The width of the annulus depends on the degree. That perhaps explains a little bit why the results are so different. I should say that Marcinkiewicz-Zygmund families for L2, well, that was my first contact with the topic. They're almost completely characterized by Groechenig, Saludes, long time ago. And I have a remark on how you see the localization and where this comes from. It's a similar computation we did 40 minutes ago for Bergman space. So I think I'm done, and I'd like to briefly summarize what I tried to communicate. One aspect is that Marcinkiewicz-Zygmund families offer an alternative method to study sampling theorems in reproducing kernel Hilbert spaces of infinite dimension, sort of the appropriate version of a finite section method in this context. And secondly, there are many questions one can work on, and we have just looked at the basic spaces of analytic functions. There's a whole industry out there asking about the discretization of LP norms. There's a different community in data science and complexity theory that has discovered this topic. I think the people have progressed so far that, at least for me, it's difficult to go into that direction. But even in complex analysis, there are dozens of variations. First of all, you can ask much more refined questions about the theorems that I showed you, and you can vary the setting For example, how about higher dimensions? Take the unit ball in Cn and look at the Bergman space. There is no sampling theorem there, or not a sharp version at least. How do you construct Marcinkiewicz-Zygmund families for multivariate Bergman spaces? And there you can, well, I think this is doable. However, you have different notions of degree, and the formulas for intrinsic reproducing kernels are much, much more involved. You could change the domain. Instead of a disk, you go to an ellipse or a rectangle. Okay, polynomials are still dense, everything fine, but you lose one important property. The monomials are no longer a simultaneous orthogonal basis for the polynomials of degree n. They are probably Array spaces, and so you have to tweak that, and I think that's quite interesting. Now there is also, you can look at generalized Fock spaces where you take the square function by some other weight. This is quite a popular topic in the work on determinantal point processes, which could be seen as random constructions of Marcinkiewicz-Zygmund families. So you have a point process that construct a finite point set, and you ask whether this satisfies a sampling or interpolation property. So that's much, much more difficult than anything I told you. And of course, you can always ask the most general question. How about working in a general reproducing kernel Hilbert space? What would you need? I think these are interesting topics to look at, and it would be nice to get in touch with people who are interested in pursuing this further. Okay, with this, I want to thank you, refer to what we have done, and thank you for your attention.
Thank you very much for a wonderful talk. Questions, comments, suggestions? Well, if there are no questions, let's thank Karlheinz again.
Okay.
And we'll reconvene